Good morning. This next unit is going to be covering chemical kinetics and chemical equilibrium. This week we will talk about chemical kinetics, which is a study of the rate at which a chemical process occurs. Please understand that this has nothing to do with the spontaneity of the reaction, just simply how quickly one will take place. Next week we'll cover chemical equilibrium to finish off our unit. The most important thing to realize about a chemical reaction is that in order for a reaction to form, the number of collisions that are occurring between reactant molecules must be maximized. So when we talk about the factors that affect the reaction rates, please always keep in mind what is going to impact the number of collisions the most. So when we first talk about the factors, the physical state of the reactants, i.e. their states of matter, is the most important thing. So try to envision which type of matter will have the most collisions. Since solids are locked in place together and cannot move very well, they just vibrate in place, they're going to have the least amount of collisions that are occurring. This is kind of counterintuitive because we normally think about, since they're so closely packed together, that they would have the most collisions, but since they are moving the least, they actually have the smallest amount of collisions. Liquids, because they are mobile, they will increase the number of collisions. However, the gaseous state is the state of matter that has the most amount of collisions because they had the most rapid movement. The other concept that we want to think about as well will be the type of compound that is present. When we talk about the different types of compounds, you hopefully remember we have ionic and covalent. Most of the time, these reactions are taking place in solution, so you have to think about what takes place with these molecules when they dissolve. So for ionic compounds, they dissociate into their ions, so they're already breaking apart into their different ions as they dissolve. With covalent compounds, they simply dissolve. The regular molecules are dissolving and staying intact in solution. So in order for the molecules of a covalent compound to actually create new compounds, they have to break a bunch of bonds between the different atoms within the molecule. So they're going to be a little bit slower in their reaction rate than the ionic compounds, because all the ionic compounds have to do is simply come in contact with another molecule and they will form the new compound. So solids are least reactive, gases are the most reactive, ionic compounds are more reactive than your covalent compounds. Okay? The more homogeneous a mixture is, the faster the molecules can react. Okay? The second factor that affects the reaction rate is temperature. Please recall from our gas laws unit that as we increase the temperature on a sample of a particle, the speed at which the particle moves increases. So if you have higher temperatures, the reactant molecules are going to have more kinetic energy, which means that they're going to have more frequent collisions and more violent collisions as well. Now, the last one here on this page, the concentration of reactants. So again, thinking about what will increase the number of collisions, if I have a greater amount of moles of my reactants, I'm going to have a greater concentration. One other thing to keep in mind when we're talking about concentrations, another way that we can do that is based off of partial pressures if it is in the gaseous state. So remember, partial pressures, essentially we could redo the ideal gas law to have moles per liter at a certain temperature equaling the pressure. So you can think about partial pressures being like a concentration. So the greater the number of reactant molecules, the more likely that you're going to have collisions that are occurring that will produce the products. Okay, so for our last two here, we can increase the rate of the reaction by the addition of a catalyst. A catalyst is something that speeds up the reaction by changing the mechanism for the reaction. Catalysts do not get consumed during the course of a reaction, they get regenerated at the very end. Now, when we talk about this whole concept of a mechanism, this is just simply a multi-step reaction that will take place to show the overall chemical equation. So if you remember back with our thermodynamics unit when we're doing our Hess's law of summation, we had those multi-step equations where we canceled off the intermediates and it added up to equal the overall chemical reaction. That is what we're talking about. This catalyst is going to change the dynamics of the reaction in terms of the energies and make it a more energetically favorable process for the reaction to take place in this alternative mechanism. So you can relate this to the little graph that we had for the energy profile diagram where we started off. Do this one for an exothermic reaction. If you recall, we'd have our reactants, we'd have our products. This part right here is the activation energy, and that's the part that we need to focus on. We have our activation energy here, and then we'd have our change in the overall energy for the reaction, which would be the delta H value, the difference between your reactants and products. Now, if this was our uncatalyzed reaction, this is what we would normally see within this reaction profile diagram. In order for the reaction to take place, we have to have at least as much energy as that activation energy that is needed in order to get the reaction to occur. However, with a catalyzed reaction, all we're simply doing, I'm going to put this one as a dashed line for that catalyzed reaction. All we're doing is we're providing a different pathway for the reaction to follow that requires a smaller amount of energy. The overall energy changes that are occurring stay the same. The delta H value is not affected by the presence of the catalyst. All we're doing is simply taking the activation energy and lowering it so more molecules have enough energy to overcome that activation energy. The last thing is increasing the surface area of your reactants. When we talk about the surface area for the reactants, if we increase the surface area, we're going to increase the number of collisions that are occurring between the reactant molecules, and as a result, you'd end up with a higher reaction rate. So this is a graph that is showing a reaction progress. You'll notice that there's a dashed line that is separating the two sides of the graph. This first side of the graph, where we're looking at the rates of the reaction, that's the side that deals with kinetics. On the right side of the graph, you'll notice here we have the equilibrium side, and that's because the forward rate of the reaction is equal to the reverse rate of the reaction. The one thing that I just want to stress at this point as we begin this type of process, just understand that it always appears as if the reaction has stopped at this point, but as long as we have some reactant molecules converting into product and some product molecules converting into the reactants, the reaction is still actually ongoing. It just appears as if no change has taken place. You would notice that because if it had completely stopped, the rate of the reaction would be on the origin here, on the x-axis here, and you would have 0 for that reaction rate. Okay, so we're going to begin by talking about the collision theory and how it relates to concentration. So the collision theory is a principle that just basically says that the particles must collide in order to react. Now, I'm going to start off by adding just a couple of extra things here. There's two requirements that must be met in order for a chemical reaction to take place. The first one is that the collisions must have sufficient energy. This one is the easier of the two to make happen. And then the second is that the collisions must occur with proper orientation. And that's the harder one for the molecules to do. So when we talk about this collision theory, again, number of collisions are occurring to make the reaction take place. An increase in the concentration will lead to a larger number of molecules and therefore an increase in the reaction rate. The number of collisions depends on the products of the number of reactant molecules, not their sums. So we're multiplying the concentrations in the rate law, which we'll talk about shortly. They're not added together. So you can see here with this slide, the number of possible collisions is going to be the products, not the sum. If you look at this first set over here, I have 1, 2, 3, 4 total molecules, 2 A's and 2 B's. So as a result, we're able to have 4 different collisions. If we were to add in another molecule of A, now I could have each of the 3 A molecules colliding with the B molecules for a total of 6 collisions. If I were to add another B molecule to the reaction mix, now I could have a total possibility of 9 collisions, 3 A's colliding with each of the 3 B's. Okay, so now we're going to talk about the amount of energy that's required and also kind of get you a beginning point of the orientation of the molecules. So you have a chemical reaction here between ozone and nitrogen monoxide, producing oxygen gas and nitrogen dioxide gas. So when we look at this reaction on the picture on the right, you can notice that a reaction can occur only if the collision energy is high enough. So in order to do this, you hopefully remember in our bonding unit, I was talking about the fact that these atoms are just kind of oscillating back and forth in place, kind of like a slinky going back and forth. We have to have the collision being strong enough so it can essentially compress those atoms together so much that when they expand back out, it snaps the force of attraction between the 2 molecules and allows a new force of attraction to be created. If there's not enough energy to make that collision occur, then the molecules will just simply bounce off each other and go in another direction. When we talk about this energy concept here, I'm going to go back and just kind of discuss, we had a Maxwell-Boltzmann distribution curve that we talked about back in our gas laws unit. So I'm going to have the number of particles over here. The ironic part of this is the fact that if you've been watching all the news on the coronavirus, when they've been talking about flattening the curve, this is essentially the same exact curve that they're talking about, just looking at it in a different form. So we have our number of particles over here on the side, and then we have a peak of the line, and then it comes out over here towards the x-axis. Now, when we talk about this, we're going to draw a line, really bad line, but we draw a line going down, and this line represents that activation energy. So that should be temperature down here. So as we look at this graph, what this is saying is that the peak of the curve, that's where we have the average kinetic energy for the majority of our particles. So the higher the peak is, the more particles possess the same amount of kinetic energy. The lower the temperature, typically the higher the peak. That's what they're kind of talking about with the curve for the social distancing part. But when we look at it in terms of the chemical reactions that are taking place, what this tells us here is that this small little fraction of the molecules that have a high enough kinetic energy to surpass that activation energy, these are the ones that could have that successful collision that are occurring at the top here if they have the proper orientation for the molecules. Now, this one here would represent a low temperature. So how does the curve shift when we have a higher temperature? So when we talk about that, because we have a higher temperature, that means that we're going to have a wider expanse of kinetic energies for the different particles. So instead of having a very tall peak that's kind of compressed, what's going to happen is it's going to spread out. It's going to be a little bit more of a gentle slope, and then it will still come down to the bottom. So what's going to happen here? The amount of particles hasn't changed, so the area under the curve stays the same. But what's going to happen is I now have a larger percentage of my molecules that now have met the sufficient energy requirement for a chemical reaction to take place. This again is by far the easiest of the two. It is just going to be a very small fraction of these molecules that have enough energy that will actually react. So these would again be the ones that would follow the successful collisions and form the products on this side. So again, this one would be the gas molecules that are found at a higher temperature. Next, we'll discuss the effect of temperature on the collision energy. So again, an increase in temperature causes an increase in the kinetic energy of the particles. This will lead to more frequent and more violent collisions and will, as a result, increase the reaction rate. At a higher temperature, again that Maxwell-Boltzmann distribution curve, the fraction of collisions with sufficient energy equal to or greater than the activation energy will increase, which will cause the reaction rate to increase as well. So again, it is just a fraction of the collisions, not all of them. But as a general rule of thumb, as the temperature increases by about 10 degrees Celsius, the reaction rate will double. This is why it's so important when you have a fever to try to get it to be lowered, because at that increase in temperature in your body, it is allowing the infection to replicate at a faster pace. Next, we're going to focus on the molecular orientation to produce an effective collision. So you can see a diagram here with a number of different collisions that are taking place. Most of them are ineffective collisions, and only one of them is an effective collision. So the first thing I wanted to do was just kind of quickly draw a Lewis structure for each of these different molecules. For the nitrogen monoxide, I would have a compound that would look like this, triple bond between the nitrogen and the oxygen. For the nitrogen trioxide molecule, I would have something that would look like this. And then finally for the NO2, it's going to have that resonance structure, alternating single and double bonds, like this. So in order for these reactions to occur, when you look at the chemical reaction, NO plus NO3 yields 2NO2. You can see here when I have this NO molecule, in order to form the NO2 molecule, I've got to have a collision occurring between an oxygen coming off of this NO molecule with the nitrogen in the NO molecule. So for this to occur, you can kind of see here, I've got two oxygens in this first one. I have two oxygen molecules that are colliding together. That's not going to work. Here I've got an oxygen colliding with a nitrogen. However, it's the wrong ones. I've got the oxygen from the nitrogen monoxide colliding with the nitrogen from the nitrogen trioxide. So that is also an ineffective collision. In this third one, I have two nitrogens that are colliding together, so that would not be an effective collision. And then over here on this next one here, I do now start to have the correct molecules, but the orientation of the molecules is not correct for them to collide, so it will not allow the reaction to take place. And finally, having the oxygen on the opposite side from the oxygen in the nitrogen trioxide, I now have the collision occurring between the nitrogen and an oxygen in the correct orientation, which will then produce the two products. So again, very few of the collisions that take place are actually in that proper orientation, but remember, when we're talking about a chemical reaction between these different substances, we typically have upwards of 10 to the 20th moles of our molecules of the particles that are colliding, so you have a lot of collisions that take place, so we can actually see some of these reactions happening in real time. Now, when we are talking about the chemical kinetics, again, we're measuring the rate of the reaction. So we have a couple of different types of reaction rates that we can measure. The first of which is an instantaneous rate. With an instantaneous rate, it is literally talking about at any point at time t in a reaction, what is the rate of the reaction. So anytime that we're talking about the rate for a reaction, we're talking about a change in the concentration. Remember, we put the concentration as brackets, so that would be, again, our change in molarity per unit time. Okay, so change in molarity per unit time. So an instantaneous rate, we can literally look at a graph for any reaction that has taken place and pick a point on that graph, and in order to find the instantaneous rate, we take a tangent line to the curve, and we find its slope. So you can literally pick a curve at any point along the curve, and you can, if I take this one right here that's already marked, I take my slope of the tangent line and I take my change in the y over my change in the x, and that will tell me what the rate of the reaction is. So that is your instantaneous rate. When we talk about an average rate, this would look at the entirety of the chemical reaction. What was the average rate that the reaction happened at? Now, a couple things. Just remember, in terms of reactants, its change in concentration is always going to be a negative because we have to consume some of the reactants in order for the reaction to take place. So therefore, as you can see here, my change in the concentration, my concentration is getting smaller over time. And then for your products, because they are being created, your change in the concentration will always be a positive value. So you can see with the two products for this one in particular, you have an increase in the concentrations, but I also want you to notice that there's a difference in the rate at which they're being produced. This is based on the coefficients from the chemical reaction. So we could say, based off of this chemical reaction that we see here, for the decomposition of nitrogen dioxide, we're going to have twice as many molecules of the NO being produced compared to the O2. So we looked at that and tried to come up with an equation. Decomposition, again breaking down, nitrogen dioxide, NO2, going to nitrogen monoxide, if you can see that right here, and oxygen gas as my two products. So if I were going to balance that chemical equation, I'd put a 2 and a 2 here. So the rate of decomposition for the nitrogen dioxide would be the same as the rate of formation of the nitrogen monoxide, but it would be twice as large as the rate of formation for the oxygen gas. So in general, when we have a chemical reaction, AA plus BB plus CC plus DD, and again, this is just a general form, so it can change depending on what the reaction is, where you have your lowercase letters, A, B, C, and D, as the coefficients for the balance equation. We can express the rate as a ratio of your coefficients, kind of treat it like a molar ratio for each of the substances in comparison to each other. So the rate of the reaction will be equal to 1 divided by the coefficient for A times its concentration change, which would also be equal to a negative for 1 over B times the concentration change of B over the change in time. It'll be a positive for C and a positive for D, again, just like we were talking about. A and B are our reactants, so their rate is going to change in a negative fashion. The products, they're going to be increasing their amount, so it will be a positive change for the reaction for that. So again, just treat it like a coefficient for your molar ratio in stoichiometry, and that will show you your relationship to the rate of the reaction. Okay, so let's look at an example problem where you can see exactly what we're talking about. It is asking you in the example problem number 1 to express the rate in terms of change in concentration with time. So you have hydrogen gas has a non-polluting combustion product, which is water vapor. It is used as a fuel aboard the space shuttle and in earthbound cars with prototype engines. So you have a balance equation, 2H2 plus O2 yields 2H2O. So the first part, it's asking us to express the rate in terms of changes in H2, O2, and H2O with time. So when we look at this, we can simply say the rate will be equal to a negative, and my coefficient for the hydrogen gas is a 2, so I put 1 over 2 times the change in concentration of H2 over our change in time. This would be equivalent to, since my oxygen coefficient is a 1, I would just have the change in the concentration of O2 over the change in time. And then because my water vapor, and that should be a negative there, and my water vapor, because it's now the product, has a coefficient of 2, it would be a positive 1/2 times the change in the H2O concentration divided by time. So we can always look at this as our relationships between the three substances. So I know that the hydrogen gas and the water vapor will form and decompose at the exact same rate, and the rate of consumption of oxygen will be 1/2 of that amount. So when I look at this as my part B, and it tells me that the O2 is decreasing at 0.23, so my change in oxygen over the change in time is equal to 0.23. Again, the moles per liter, remember that is your molarity, and that should be seconds to the -1. So I'd have my change as molarities per second. When I look at that information, I know that the rate of the O2 is 1/2 of the rate of the H2O, and so as a result, I could simply take this, set that equal to 1/2 the change in the concentration of the H2O over our change in time. To get rid of the 1/2, I would multiply both sides by 2, and so I would end up with 0.46 molar per second as the rate of formation for the water vapor. Okay, so the whole point of this is to show the relationship between the different reactants and how their changes in concentration will affect the rate. We call this a rate law or a rate law expression, or a rate expression. So anytime that it asks you to do something about solving for a rate law or a rate law expression, we're simply putting it in this form here, where we have the rate equals K, which is a rate constant, times the concentration raised to a certain power. We call that certain power that we are raising the concentration to in order for the reactants. We only focus on the reactions that are taking place at the very beginning because we don't want to see how the product collisions will affect the reaction rate. So we always look at these at the very beginning of the reaction, so as close to time t equals 0, to see how the change in concentration will affect the rate of the reaction. One other thing, these are always found under experimental conditions. The coefficients have no impact on what the orders are. Sometimes it will work out where the order will match the coefficient, but it doesn't always happen. So again, the reason why, when you think about those multi-step reactions, you could have, like in this example, the NO2, it could be having one of the NO2 molecules react at the beginning step and then a second molecule that would react in a later step further down. So when we talk about the rate, you're going to see something called like a rate determining step, and that is essentially the slowest step in the process. And so the chemical reaction will be limited by how quickly that slowest step occurs. So for the orders, the exponents that we're raising the concentrations of our reactants to, they can have a number of different values. They can be negative values, they can be fractions, but typically we're only going to work with first, second, and zero order reactants. When we talk about a zero order reactant, this is going to be a reactant whose concentration changing has no impact on the reaction rate at all. So if you think about any type of number that we would raise to the 0 power, so say I have a concentration change that's tripled, so I have 3 times the amount of the concentration of the reactant. If I raise that to the 0 power, it still equals 1. So no matter what we do to the concentration, the reaction rate stays the same. Typically, when you have that zero order reaction, this reactant is introduced after that rate determining step. If we have a first order reactant, that means that changing the concentration will cause a proportional change in the reaction rate. So again, it'll be directly proportional. So i.e. if I double the concentration change, then that's going to double the reaction rate. So whenever we're talking about this, the number that we put down here on the bottom as the 3, when we look at that, that's talking about what change we have caused. So in this case, if I have a doubling of the concentration, that would be essentially raising 3 to the first power because it is a first order reactant. And so anything raised to the first power is itself. So therefore, if I triple the concentration, I triple the reaction rate. And if I have a second order, that means again that we're going to be squaring the change in the concentration. And as a result, you'll have your reaction rate increase by a square of that change. So if I take a tripling of the reaction rate, as you can see here, and I square that, that means that my reaction rate will increase by a factor of 9. Okay, so this would be, again, the concentration change right here, and this would be the change in the reaction rate as a result. So a second thing that you may be asked to solve for is the overall reaction order. The overall reaction order is simply a sum of the exponents in the reaction rate equation. So for the rate equaling k times a raised to the n and b raised to the m, the overall reaction order would simply be the n plus the m. So if I looked at something like this where we had, say, rate equals a squared times b, again, we can infer that the b has a exponent of 1. It is not necessary to write it. So in this case, I would simply have 2 plus 1. I should have a k there. So my overall order would equal 3. You can also be asked to solve for the value for the rate constant. And for that, it's just algebra. You would take to isolate k, you would take the concentrations of A and B raised to their certain powers and divide the rate by it. The one thing that does change, though, is the unit of k. The way how you can figure out the unit for k is pretty simple. Take 1 and subtract whatever the overall order is for your reaction. The reason why, when we set this up, again, remember the rate is in some type of form of molarity per unit time. So I have a molarity in the numerator, and then I would be dividing it by the number of molarities for my concentrations powers being raised. So remember, for your law of exponents, if I'm dividing numbers, I would subtract them. So in this case, I have 1 for the molarity from the rate minus 2 plus 1 for a total of 3. So 1 minus 3, my unit for k for this particular example here, I would have m to the minus 2, and then I have my unit of time, whatever that is, minutes, seconds, hours, to the minus 1. And again, it's minus 1 because it's in the denominator. So I can have m to the minus 2, m to the minus 1. So for the unit of k for your reaction, simply take 1 because of the rate molarity and subtract the overall order, and that'll tell you the unit for k. We have a number of different methods that we can use to determine the rate law for a particular reaction. We are going to focus on one for this class, which is called the method of initial rates, or the differential rate law. With this differential rate law, as we were mentioning earlier, we're going to look at the initial rates of the reaction as close to the time t equals 0 as possible. When we do this, we're going to conduct several different experiments where we're going to change the initial concentration of one of our reactants only and see how that change in the concentration will affect the rate of the reaction. This is done experimentally, as I said, so please understand that you will get a little bit of error. It's not always going to be a perfect multiple, but it should be very close. So instead of, say, 2, it might be 1.97. you are allowed to just round it up to 2 because it's essentially showing us that it is doubling the reaction rate. Now, the other method that we can use is something that we call the integrated rate law. When we look at the integrated rate law, this shows us how the concentration changes over time. This would be something that you would cover in AP Chemistry as a second method for discovering the rate law for the reactions. But again, we will not do that in this class. So you'll be given data about the concentrations and the rate of the reactions for multiple trials of the same reaction while keeping the temperature constant. Please be very vigilant with that. The temperature must be held constant because the K value, that constant, only changes with temperature. So as a good scientist, we want to only change one concentration at a time in order to determine the impact of that one particular change. So we have two different options that we can use to solve these types of problems. We have an algebraic method, which is just simply going to be math, taking two of the equations for two of the trials and setting them equal to each other and seeing how the change in the concentration affects the rate. Or we can use what's called a table logic method. The table logic method, I highly recommend getting used to it because especially if you would have multiple choice questions, you can do these very fast and get through the work very quickly. However, you have to write a little 1 to 2 sentence blurb explaining what you did to determine the order for each of the different reactants. So I'm now going to start working through some practice problems, and I'm going to show you using these different methods how they can be completed. Okay, so the first example problem, I'm going to use the algebraic method. We have 3 different experiments that are being run, and we have changes in the concentrations of NH4 plus, and looking at this table here, this NH4 or NH2 minus should actually be NO2 minus instead from our balance equation up here at the top. So we have concentration changes for each of these two substances, and we have changes in the rate of the reaction. Now, when we are looking at these things, I would highly suggest a couple of different things for you. Number one, because you guys don't normally like working with fractions, I would always look at your rates of the reaction and place the larger of the two rates in the numerator. That way when you divide them, you'll always get a number greater than 1. The second thing, in this example, you have all of your exponents being equal to each other. So when you're doing that, it's not a big problem, but if you have different exponents, I would highly suggest altering what the exponent is and then changing the number out in front to make all of your exponents equal to each other. So just for example with that, say that this first one was 1.35 times 10 to the minus 6. I would change that and say 13.5 times 10 to the minus 7th. That way you have all the exponents the same and you can just compare the numbers that are out in front. Okay. So as we begin to look at this algebraic method, we need to solve a problem for each one. The overall goal is to solve for the rate expression. So again, I'm going to have it in the form of the rate equaling the K times the NH4 plus raised to some power m and the NO2 minus raised to some power n. If we had more reactants, the next one that we would do we would raise it to the P, because we don't want to raise it to O because that would look like a 0. So we'd go to that next one, which would be the P. But you can use ABC, you can use WXY, whatever you want to do. But I would not use the O because it looks too close to a 0. So I'm going to start off looking at figuring out the concentrations power for NH4 plus, the ammonium ion. So to do this, what I want to look at is finding 2 of the 3 reactions where the NH4 plus will stay, will have a different concentration, while the NO2 concentration will be held constant. So if you notice, I have 0.010 molar for each of these two concentrations of NO2 minus for these two trials. So I'm going to choose trials 2 and 3. You'll notice here that the 5.4 times 10 to the minus 7th is greater than 2.7 times 10 to the minus 7th. So I'm going to start by placing rate 3 over the rate 2. When I set that up, that would now give me 5.40 times 10 to the minus 7th divided by 2.70 times 10 to the minus 7th, and that is equal to K. And I have now the NH4 plus, which is equal to 0.200 for rate 3, times the NO2 minus, which is equal to 0.010 for our third experiment, excuse me. I'm going to raise those to the M and the N powers. And then for rate from experiment 2, again, we had the K value, we had the concentration of the NH4 raised to the M, and that is 0.100, and then we have the NO2 minus, and that is 0.010 raised to the N. So since I have 0.010 raised to the N for each of these, they will cancel off. That's the importance of having them held constant. The K, because the temperature is being held constant, the K for the reaction will stay the same. And so now I have my ratio here, 2 for the change in the rate, 5.4 divided by 2.7, 10 to the minus 7ths cancel off, so that's equal to 2, and that's now equal to 0.200 raised to the M divided by 0.100 raised to the M. So hopefully you can see here, 0.2 divided by 0.1, that's equal to 2 raised to the M power. So now when I set this up, in order to solve for the order, 2 raised to a certain power equals 2. So I know in this case my M has to be 1. So the NH4 plus is a first order reactant. So I'm now going to do the same thing for the NO2 minus. I need to look here and I need to see what I can do to change the reactions and keep the NH4 constant now while we change the concentration of the NO2 minus. So hopefully you'll notice experiments 1 and 2, concentration of the NH4 plus is held constant while the concentration of NO2 minus is changing. So in this case, 2.7 versus 1.35, I'm going to place the rate 2 in the numerator and the rate 1 in the denominator. So I would have 2.70 times 10 to the minus 7th divided by 1.35 times 10 to the minus 7th, and that is equal to the K. Now, since we've already solved for NH4 plus, if you want to put it in as being a first order, you're welcome to, but you don't have to. And we're just going to repeat the process, but this time solve for the NO2 minus. So for this one we had 0.100 and 0.100. Those again will cancel, as well as the K's. Now for the NO2 we had 0.010 and 0.005. So in this case here, again looking at our numbers, 2.7 times 10 to the minus 7th and 1.35 times 10 to the minus 7th, that divided out would equal 2 for my change in the rate. And then I have 0.010 raised to the N divided by 0.005 raised to the N, so that once more also equals 2 for my change in the concentration raised to the N power, equaling 2. So I know in this case my N would equal 1. So for both of these substances, they are first order. So my final answer to the rate expression, I would just simply say rate equals K times NH4 plus times NO2 minus. If it asked you for the overall order, I'd have 1 plus 1 equals 2. If it were asking you to solve for K, you can just arbitrarily choose one of the three trials. Now that you know the orders, you could just plug in the concentrations into the expression and set it equal to the rate. So for our second example, I'm going to go ahead and use the table logic method to solve these problems. So for that table logic method, we're basically doing the exact same thing, except we're just going to use the data points from our table to make our comparisons, and we're not going to actually write out the algebraic work. We're just going to put a 1 or 2 sentence blurb out there to describe what we're doing. So in this case, we have some reaction between A and B that's taking place. They tell us what the initial rate is in molarity per second, and then we have an initial concentration of A and an initial concentration of B. So I'm going to start off solving for the initial concentration of A. So same type of concept. We're going to simply be looking at two of our reactions that are taking place, looking to keep B constant while A changes, and then comparing the rate change to the concentration change. So for A, I'm going to choose experiments 3 and 4. We can just simply say that the concentration of B is held constant. And if we look at the concentration change of A, I went from 2.5 to 5.0 times 10 to the minus 2. So that would represent a doubling. So I can just say 2x for the change in the concentration. And then my change in the rate, 3.5 to 7, also doubles. So I can say for the concentration of A, we chose experiments 3 and 4, B is held constant while the concentration of A doubles. We can say the reaction rate doubled as a result. Therefore, we can take 2 raised to the m power equals 2, so m equals 1. So I can just simply say A is first order. Now, when we look at B, we're going to do the same thing, and this time we're going to try to find a reaction where A will stay constant while B will change. So I'm going to choose experiments 1 and 3. So you can see here, A is held constant, so it's still just 1x. My concentration change for B, I went from 3 times 10 to the minus 2 to 6 times 10 to the minus 2. So that doubled. And now my change in concentration, or change in rate, excuse me, 1.75 times 10 to the minus third, going to 3.5 times 10 to the minus third. That would represent a doubling as well. So I would just simply say for B, we chose experiments 1 and 3. The concentration of A is held constant, while the concentration of B doubled. As a result, the reaction rate doubled. Therefore, we have 2 to the n equals 2, so n equals 1, and B is first order. Now, like I said, from a multiple choice standpoint where you don't have to show any of your work, this table logic method is much faster because you don't have to write out this little 1 or 2 sentence blurb about what you did. So that it is advantageous to be able to do this method and quickly rationalize what's taking place. So our final answer, we would have rate equals K times A times B. Our overall order would be 2. So I'm going to do a second problem using that table logic method. So for this problem, it's asking us to determine the rate law expression and solve for k based on the following data. So now this is going to be the first time when we're actually going to solve for k as well. So to do this again, I need to look at my initial rate, which is again in molarity per second. And then when we do this here, we have our change in concentration of oxygen and our change in concentration of nitrogen monoxide, our two different reactants. Now, as we begin this process here, again, I'm going to start solving for the O2. So for the O2, I want to find one where the NO is being held constant. So reactions 1 and 2 look good for that. This one is just a change in X. This would be 2 times X. And here we'd also have 2 times X as well. This is what I was talking about. Notice 6.4 divided by 3.21. That's not going to be exactly 2, but it's going to be like 1.97, something like that. So we can just round it to 2. So for this one, I would just simply say chose experiments 1 and 2. The concentration of NO held constant, while the concentration of O2 doubled. As a result, the reaction rate doubled. Therefore, we have 2 to the m equals 2, so the O2 is first order. Now, going on and doing the NO, now I want to choose an experiment in which the concentration of O2 stays the same while the concentration of the NO changes. So as I look at a couple of choices for this, we want to find one where the O2 stays the same. So we can do experiments 1 and 3. So here, again, I have just a change of 1x. Over here, I have a change of 2x. Now, for my rate, notice it's going from 3.21 to 12.48. Again, pretty close. So we're going to call that 4 times x. Probably about 3.9 approximately for the change. So we're going to round that up to 4. Okay, so for NO, we would simply say we chose experiments 1 and 3. O2 concentration held constant, while the NO concentration doubled. As a result, the reaction rate quadrupled. Therefore, we have 2 raised to the n equals 4, so n equals 2. So my overall answer, I would have rate equals the K times the O2 times the NO squared. So the overall order would equal 3. So now for the second part of the problem, it's asking us to solve for K. So if I were to rearrange our equation, I'd have the rate divided by the O2 and the NO concentration squared. So like I said, it is completely your choice which one of the experimental trials you decide to use to figure out your values. They should all come out to be relatively the same thing. So I'm just going to arbitrarily choose reaction number 1. So for the rate, so for experiment number 1, we had a rate of 3.21 times 10 to the minus third. So I'm going to take my concentration of the O2, which is 1.1 times 10 to the minus 2, and we're going to multiply that times the NO concentration, 1.3 times 10 to the minus 2, but because of the order being second order, we're going to square that value. So if we type those in, 3.21 times 10 to the minus third divided by 1.1 times 10 to the minus 2, and then divided by 1.3 times 10 to the minus 2 squared, we end up with a value equal to 1727. We have 3 significant figures, so we'll round that to 1730. So again, remember, for your unit of K, we can take, for that unit, 1 minus the overall order, and that will be what we raised the molarity to. So we had an overall order of 3, so 1 minus 3 is negative 2. So I'd have m to the minus 2, and then your time component always will be to the negative 1. So our final answer, 1730, m to the minus 2, s to the minus 1. So for example problem number 4, I'm going to go back and work this one out using the algebraic method. So this one is asking us, many gaseous reactions occur in a car engine and exhaust system. One of these is NO2 plus CO, forming NO and CO2. It tells you the rate is equal to K times NO2 raised to the M power times CO2 raised to the N power. So we want to use the following data to determine the individual and the overall reaction orders. So again, 2 parts to this problem. So for that algebraic method, I'm going to start off looking at the NO2. So for the NO2, we want the CO to stay the same. So if you notice, experiments 1 and 2 both have the concentration of CO being held constant. So now I have this part over here with my rates. 0.08 is greater than 0.005. So I'm going to put rate 2 on the top and rate 1 on the bottom. So 0.08 divided by 0.005, that is equal to 16. So that's now going to be equal to my K's, my rate 2. I have the NO2 concentration as 0.40. I'm going to raise that to the M power, and CO we had as 0.10 raised to the N. For rate 1, the NO2 was equal to 0.10, and the CO is still 0.1. So again, the 0.1 raised to the N power, both of those cancel. My 2 K's cancel. So now that leaves me essentially with 16 equals 0.40 and 0.1 raised to the M. So I have essentially 4 to the M power equals 16. So I know my M is equal to 2. So I know NO2 is a second order reactant. So now when I come and look at the CO, for this one, I want to choose 2 reactions where the NO2 is held constant. So that would be reactions 1 and 3, while the CO changes. So now when I look at this here, you'll notice I have the same exact rate, 0.005 and 0.005. So I don't technically have to do anything with this problem to figure it out, but I'm going to show you mathematically just so you can see. So in this case, it doesn't really matter which rate we put on top, but I'm going to go ahead and put rate 3 on top and then rate 1 in the denominator. So I have 0.005 over 0.005, so that equals 1, and that's equal to my K. We have our NO2, and I'll raise that to the M, CO raised to the N. We know the NO2 is second order, but that does not matter for us in this case. So for our concentrations, the NOs NO2s are both 0.10, so those would cancel, your Ks would cancel, and then I would have 0.20 over 0.10. So essentially I have 1 equals 0.20 divided by 0.10, both raised to the n power. So 2 to the n equals 1, so I know in that case that my n equals 0. So in this case, the CO equals a 0 order reactant. So for our rate expression, because it's 0 order and anything raised to the 0 power is equal to 1, you can simply exclude it. So we could say rate is equal to K, forgot the K, times the NO2 squared. Or if you wanted to include it, you could simply say rate equals K times NO2 squared times CO to the 0 power. But again, that would just simply cancel off. So you'd have that as your rate expression. So that would be the answer for the first part. And then the second part, asking for the overall order. Since I just have one, the overall order, one reactant, I'd have 2 plus 0, which would equal 2. Okay, so our last problem is going to be kind of a challenge problem. With this one, you have data for the reaction 2A plus B forms 2C. It asks you to find the rate law and find K with units. When we look at our data table, you'll notice we have a small problem. When we have our initial concentrations of A, I have 2 trials that are held constant. But when we look at B, we have no trials that are held constant. So we're going to expand this out and we're going to make what we call an expected table. So we're going to take the information that we have available to us and we're going to solve for the order of B to begin with. And once we have B, we can see how that changing concentration here, what we would do to make 2 of them equal to each other, how that would affect the rate of the reaction. So for this, we're going to come back. I'm going to put an asterisk there so we can see it here. I'm going to again use the table logic method to figure this out so that we can then come back and solve the problem. Okay, so for our first part, determining the order for B. Looking at our trials, you'll notice that my A concentration is held constant in trials 2 and 3, and my concentration of B doubles. So for this one, I can say chose experiments 2 and 3, concentration of A held constant, while the concentration of B doubled. Our reaction rate, 3600 to 14,460, this one is going to represent a 4-fold increase. So for this one, we have the concentration of B doubling, the reaction rate quadruples. So therefore, we have 2 raised to the m power equals 4, so m equals 2. So I know in this case, I'm just going to write that over here on the side, B is a second order reactant. So here's where we're going to use this information to our advantage. Okay, so we know based on our initial talk about the reaction orders, any change in concentration for a second order reaction is going to raise that change in concentration to the second power. So when I try to figure out the order for A, I'm going to look at experiments 1 and 2. So when I look at 1 and 2, my concentration here tripled for A, but I'm going to try to manipulate my data to make 2 of my concentrations for B equal to each other. Now I could either divide the second trial by 2, or I can multiply the first trial by 2. So I'm going to take this and I'm going to multiply it by 2. When I do that, that gives me 0.40 for the molarity of B in trial number 1. However, because I doubled my concentration, and knowing that B is a second order reactant, I know that that would mean that my initial rate, I'm going to take that concentration change and doubling it, which is essentially multiplying it by 4. And so that's going to make my rate become 1200. 4 times 300 gives me 1200. Now I have enough information to make my comparisons, because I can now see, because these two things would be held constant to each other, I can now see how just that change in A would affect my reaction rate. So for A, we could say that we chose experiments 1 and 2. We can say that the concentration of B in experiment 1 is doubled. Causing it to equal the concentration of B in experiment 2. And then from there, we can say that the concentration of A is tripled. The reaction rate initially in experiment 1 was multiplied by 4. Again, that's since B is second order. And so as we compare 1200 to 3600, the reaction rate overall tripled when the concentration tripled. Therefore, we have 3 raised to the n equals 3, so our n equals 1. So A is first order. So this is a complicated problem to do. So my answer overall for part A, I'd have my rate equals the concentration of A times the concentration of B squared. Now for the last part, solving for K. So once more, I'm going to take my rate, divide it by the concentration of A and the concentration of B squared to equal K. So I can choose any of my trials. It does not matter. So I'm just going to arbitrarily choose trial number 1 again. So for this one, I'm going to do experiment number 1. So my value here for K, I have the rate being 300 molar per second. I would divide that by the concentration of A, which is 0.10, and then I have my concentration of B, which is 0.20, but we would square it. Okay, so I take 300 divided by 0.1 divided by 0.2 squared, and we end up with your K value equaling approximately 75,000. I have an overall order 1 plus 2, so that would be 3. 1 for the rate molarity minus 3. I would have, once again, m to the minus 2, s to the minus 1. So take a moment, pause the video, and try to do this last problem here. How do the exponents or the orders in a rate law compare to the coefficients in a balanced equation? So pause the video, try to answer it. Your answer is simple. There is no relationship between the exponents or the orders in our rate law compared to the coefficients. Again, the reason why is the fact that these reactions take place. Oops, let me change that out. Our reactions take place in multiple steps. Not just in a single step. Typically, the most that we can do is have two molecules collide together to have the appropriate orientation for the molecules to create the products. Anything above 2, 3, 4, 5, now you're talking about having better chances of winning the lottery than you do of a reaction taking place.